determination of, write down determination of the acceleration, determination of the acceleration due to gravity, due to gravity, due to gravity using the simple pendulum. Determination of the acceleration due to gravity using the simple pendulum. Okay. So we are going to determine acceleration due to gravity. Acceleration due to gravity is gravitational acceleration, right? Using a simple pendulum. So here, using this experiment, if you want to find the gravitational acceleration on the moon, you can find that, right? On the moon, if you do this experiment, you can find the gravitational acceleration there. But here, we are doing the experiment on Earth, right? So we are going to find the gravitational acceleration on Earth. But for any other gravitational accelerations also can be found using this same practical, right? I think you referred the notes. You know what a simple pendulum is, right? There's a string and there's a small bob at the end of the string, and the string is hanged to a ceiling or something. Then what do? You pull the string aside, I mean bob aside, then leave it, right? Then it causes a oscillation. That oscillation has a time period. That time period is found using this equation. T equals 2 phi L over G, right? So simple pendulum is something like this. Then it goes to this side and comes here, goes here, then comes back to the initial position. So one of these oscillation, the time taken for one oscillation is what we call a time period, right? I'm not going to explain the theories. I'm going to focus on the experiment, right? Right. So this is the equation we used in the experiment. So before doing the experiment, we have to make sure that this is a simple pendulum, not just a pendulum. This is a simple pendulum, right? So if it is a simple pendulum, let's say simple pendulum, this string should be light. This string should not have any mass, right? Not mass, I mean this should be weightless. This string, not the bob, this string should be light. Light string. And the another condition is inextensible. Inextensible. So the length of the string remains the same, right? It doesn't extend. Okay? This should be inextensible. Actually, we cannot have a light string. These have weights, right? But in order to do the experiment, we have to make sure, compared to the bob, the weight of the string is negligible. So in that case, we can consider this to be a light string, and also the string should be inextensible. So those are the conditions to make this a simple pendulum, right? Right. Then to use this equation, another requirement is upthrust. Negligible upthrust and resistive force. Resistive force should be negligible, right? Upthrust also should be negligible. You know upthrust, U equals V rho G. We have to make sure that the upthrust is negligible. So we cannot use this equation inside a liquid, right? We have to do this in air or a vacuum. Then we can apply this equation. So we can say upthrust is negligible. So for the upthrust to be negligible, you know upthrust is V rho G. Volume of the bob, this is the bob, we call this bob, right? Volume of the bob should be negligible. So for this small bob, we need a small bob. Okay, so in order to have a negligible upthrust, we need a small bob. So we can say upthrust is negligible. Another thing is, in order to have the resistive force, a small resistive force, that bob being is small also helps to decrease the resistive force. You know, when a large ball moves through air, there's more resistance, air drag, right? But if you have a small ball, then it has a less resistive force. So under these conditions, you can apply this equation. Another thing, right? Another thing, small angle. This angle should be 5 degrees or 6 degrees. 5 or 6 degrees. You know, when you have to drag this bob to one side, right? This angle cannot exceed 6 degrees. If you exceed 6 degrees, this is not a simple, there's no simple harmonic motion here, right? We call this simple pendulum because we consider this to have a simple harmonic motion. But if you give this a large angle, initial angle, then the oscillation would be like this, right? So this type of oscillation, we cannot assume that there's a simple harmonic motion. Simple harmonic motion happens like this, in a straight line. Only if this angle is very small, you can assume that this to be a simple harmonic motion. So the angle should be 5 degrees or 6 degrees, right? Okay, just take this down quickly, right? So as I am explaining, you can take down the notes, right? If you think something is important, something on the board or something, you can take your own notes. Quickly take this down, and as I'm writing, you can take it down. And thumbs up once you've taken it down. And if you have any problem, let me know. Okay, so it seems everyone has taken it down. There is another important fact, right? These are the questions they ask in the exam, right? So here, this length is the length of the string, not the length of the string. This length is what? Length from here to here, actually. Here to the center of gravity of the bob. This length, right? This L means string plus radius of the bob. You have to think about the oscillation of the center of gravity of the bob. Otherwise, it could cause an error. Sometimes they consider the radius of this. In some cases, you can neglect the radius. But if they say you have to consider the radius, you have to consider the radius, right? So let's say a length of the string is L dash, then the length to be substituted here should be what? L dash plus R. L dash plus R, right? Draw this one as well. Put a point here. Quickly draw this. Thumbs up, right? Once you draw it. Uh, another fact is, why do we take a spherical shape? We can take like a lentil shape or something like this. But we take a spherical shape. What's the reason? For our spherical shape, the position of gravitational acceleration can be found, right? Easily. Because we need to find this exact position here. So you can easily measure this length, right? So write this fact as well. Write down in front of this uniform shape. Here we choose a spherical. What's the reason? To guess G easily, right? To guess gravitational center of gravity easily. Okay, this is like the summary, right? Summary of the conditions required there. All this is to make sure that you are using a simple pendulum. This should be not just a pendulum, this should be a simple pendulum which has a simple harmonic motion, right? So all these are based on simple harmonic motion, right? Right. Draw a line below all these like this. Just draw a line. So to again emphasize this, I'll give you a note. Quickly take this down, right? Right. Draw a line. Below that line, right? First point. Write down. So as you are writing, you have to understand, right? You don't have time to later prepare this. So as you are writing, understand this, right? Okay. Write down the experiment. The experiment is based on. The experiment is based on t equals 2 pi L over G root. The experiment is based on t equals 2 pi L over G root. To the same line, right? It is valid for a simple pendulum. It is valid for a simple pendulum under negligible quickly take the note, right? Under negligible upthrust, comma, resistive forces and for oscillations of small angles, okay? Below that, right, number 1, under that, right, further explanation, under one, simple pendulum should be made using a string that is light and inextensible as much as possible. Okay, everyone, speed is okay, right? Right. Then the second one, right? Quickly take this down. It doesn't have to be nice letters, right? Just take it down quickly. Second one, under the main thing, second one. When Bob is small, upthrust and air resistance is lower. To the same line, right? If necessary, resistance can be further decreased if the bob is given a lentil, right? Lentil like shape. Lentil means like this, right? This shape, we call this lentil like shape. If you want, you can draw this. Then third one, write down. Pendulum is to be moved. At small angles. Within brackets 5 degrees or 6 degrees. 5 degrees or 6 degrees. Five degrees to 6 degrees. Everyone done? Thumbs up, right, if you're done. Done writing. Right. So now I have discussed the requirements in order to make a simple pendulum, right? So those are the conditions that you need to You have to make sure that these requirements are met in order for this before doing the experiment, right? You have to consider these. They ask questions on this, right? Okay. Then we have this experiment. We do this experiment using a graphical method. Okay. So the first part is over now. Now we have to think about why do we use a graphical method for this experiment. You might not know the reason. The experiments are given, but some experiments have graphical methods. Some experiments don't have a graphical method, right? Actually, there's a reason for that, using a graphical method. Okay. Then we have to discuss that. You know that, so this is the equation, right? This is the equation. So what do we have to do? We have to find this simple g, gravitational acceleration. We can measure length, right? We can measure the length. We have to find g. We can simply measure the length. And you just give this oscillation, and using a stop clock, you can measure t as well. You can measure time period and length. Then just by substituting these in this equation, you can get a value for gravitational acceleration. You can get a value for gravitational acceleration, right? But we are using a graphical method. Why is that? Why do we have to do this same thing? Like we have to take like 6 readings, right? Then you have to get 6 different values for L and 6 different values for time in order to draw a graph. Here, the reason is to minimize random error, right? So if they ask in the question, why go for a graphical method? So one reason is to minimize random error. We can get rid of random error completely but we can minimize the random error. So what is random error? So if we take like let's say this is the accurate value, right? Right in the middle, accurate value. But in the experiment, you get values like this. So in this case, determining, let's say you got just a one value here. There's a gap here, right? But in order to minimize this, if you consider many values, in order to find the same thing, it gives us a more accurate answer. It is like finding the average, right? When you are finding the average also, rather than determining a value using just a one x and y coordinates, it is better to determine the same thing so we can make sure that the value is accurate. So graphical method is something like that, right? So we have about 6 readings, x and y coordinates, which says about the same thing. So this is, we are making sure that g to be correct value. So that is the reason using a graphical method. It is true for this practical and for other practicals as well, right? So if they ask, you just have to say to minimize random error. Right. So that is one of the methods. I give you a note on that, right? Don't worry. There's another important thing that we have to talk about. So this is 2 phi. You can write g here, like root g, and L here, right? L here. You can choose this value to be the dependent variable to be y, right? And this root L to be the independent variable. And this becomes the gradient, simple M. So we have a y equals mx graph. In order to have the graphical method, you need to have a y equals mx, so mx plus c. But this is not correct. This is less accurate. The more accurate method is, so in the book you can see, they have squared both sides, right? Squared both sides. What do you get when you square this? T squared 4 phi squared divided by g and L. This one is less accurate. This one is more accurate. So we are choosing t squared to be y, not t. Mathematically, we can choose this one and this one as x and y. But it is less accurate, right? Therefore, we are using t squared and L to be the x. Then gradient becomes mx. So this is more accurate. Okay. This is more accurate. Okay. If you want, you can take this down. So if they ask, why do you have to square both sides? You just can say this is more accurate. We can derive why this is more accurate, right? But that is not on the syllabus. Rather than using these ones, all you have to say is this method is more accurate, right? By error analysis, you can explain why this is more accurate, but that is not necessary here. You just have to know this one is more accurate. You can take this down. This is the another point, right? Right. Below this, take down this note. You can draw a line, take down this note. For simple L and capital T, values can be substituted in T equals 2 pi L over G root and the value of simple g can directly be found. But using a graphical method, minimizes the effect of random error. So if someone don't remember those stuff, random error, system errors, I'll be doing a lesson in the future, right, on errors. Then another point, write down result gained by the graph t squared with, right, t squared with L, t squared with L is more accurate, is more accurate than the graph t with root L, t with root L, t versus root L, right? So we are going for this one, t versus root L. Okay, so that is another important fact, right? Then we are going to move for the another one. You might have heard that you have to take, when you are measuring the time period of this one, it is better to take, if you take like just a one oscillation. Let's say it moves from here, it starts from here, 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 then comes here. Time for a one oscillation. We can measure using a stop clock. But this is not, this is a less accurate method, right? So what do? We measure time for a 25 oscillations. It doesn't have to be exactly 25, but recommended amount is 25, right? You measure the time for 25 oscillations. So you have to wait till this makes 25 oscillations. Then what do? You divide that by 25. That time divided by 25 in order to find the time period. So you can see this one is somewhat accurate, right? Rather than thinking about a one oscillation. So the human error, there are many errors like that. Human error, because we cannot start just right at this point, right? Stop clock. So it is better to measure the time period for a 25 time for a 25 oscillations. That's the reason there, right? So the time period is capital T, measurement is simple t. Okay. Draw a line like this above, just draw a line to separate the above stuff. Write down y measure, y measure okay, we'll see. Write down y measure the time for 25 oscillations. Y measure the time for 25 oscillations? Question mark. Okay. Okay, so this stuff is very important, right? Carefully listen now, right? Now carefully listen. Let's say time period. Let's say time period is capital T. Number of oscillations is capital N. If you want, you can take it down. Time for capital N oscillations. Let's say simple T. This is what we call time measurement, right? Time measurement. Take this down. You have to clearly identify these terms. So capital T is time period, that is for a one oscillation. Capital N is number of oscillations, meaning 25, right? This can be any other value. Simple T is the time you have to wait till all 25 oscillations or n number of oscillations. That this is what we measure. Simple t is what we measure, right? Taken this down. Thumbs up, right? Okay. Then we can write this equation, right? We can write this equation. Time measurement, this is the time for 25 oscillations, right? Should be equal to what? Time for one oscillations times n number of oscillations. Do you understand this equation? You don't have to remember this, right? These are, you have to understand this, right? So the time measurement is time for one oscillations times number of oscillations is equal to t. Then we can get delta t equals capital N delta capital T. So these two are the variables, right? Simple T and capital T. This is a fixed value. 25, it could be 40. This is a fixed value. These are the variables, simple T and capital T. In that case, you can write delta T. This can be done for any equation, right? If you find the variables, you can put delta there. If you're a maths student, you already know what's the reason. But for bio students, just remember, if these are the variables, you can put delta and make a new equation, right? Okay, so delta t equals n delta t. Then what I'm going to do is, I'm going to divide this equation both side by simple t. So instead of simple t, I can substitute what? Capital NT, right? Instead of simple t, that is capital NT. N cancels off. So what do we get? Delta t divided by t equals delta t divided by capital T. This equation, even if you remember, it's better to remember this one. Just take this down. I'll explain what this means, right? Take this down and thumbs up. You should be able to prove this. Right. So what is fractional error? When you are doing experiments, you should be able to know what fractional error is and percentage errors, right? So fractional error is error divided by, if you want, you can take this down. Fractional error is error divided by measurement, right? Usually, for error, we substitute what? Least count. Least count. So for a meter ruler, least count is 1 millimeter, right? The least amount that you can measure using that measuring instrument. That is the least count. You substitute it here. Then this is the measurement, right? So you know, usually this fractional error has to be less than 1%, right? So what is delta t divided by t? Delta t means fractional error of simple t measurement. You have to understand these are two different things, right? Simple t means time for 25 oscillations. Time for 25 oscillations. So that is a different measurement. So in this says fractional error for simple t is equal to what? Fractional error for time period, right? That is what this means. Fractional error for simple t equals fractional error for time period. take this down. Okay. So the reason for using going for 25 oscillation is to decrease the fractional error, right? So here what is the measurement? Error means, let's say the least count. We use in order to find the time measurement, we use a stop clock. We use a stop clock, right? So for a stop clock, uh, the least count is 0.5 seconds, right? In the lab, it is 0.5 seconds, least count. The measurement, let's say the measurement is like 50 seconds, sorry, 2 seconds. This is for a one oscillation. But if you take 25 oscillations, what happens? The denominator is higher. So the fractional error decreases, right? That's the reason why you have to go for 25 oscillations. So the measurement is larger. Then that measurement, that fractional error is equal to fractional error of the time period as well. We prove that here. Okay. Right. Take down this below everything. Take down this. Write down. By measuring time within brackets simple t for 25 oscillations rather than measuring time for a one oscillation. For a one oscillation, reduces fractional error of time measurement. Fractional error of time measurement. Draw a line below that. So I'm going to discuss the next one. Uh, Below that line, put this point. Just write this down, then I'll explain. For a certain simple L, time within brackets simple t, for 25 oscillations, should be gained three times to the same line, right? The certainty of readings, certainty, right? Certainty of readings can be increased and a better average can be estimated for the time period for the time period. Okay, done. Right. So let's say you have a simple L value, right? Let's say like 1 meter. So you have the pendulum which has a 1 meter length, let's say, right? These are not exact values, just let's say. So now you have the pendulum, let's say it is 1 meter. I'll put simple L. You have to measure the time for 25 oscillations. Let's say you get T1, T2. You do the experiment once, right? For 1 meter, you measure the time for 25 oscillations. That time is T1. Then you again do the same thing, right? Without changing anything, you do the same thing. And you get another value for time. Let's say that is T2 for 25 oscillations. Then again do the same thing. You get another reading T3 for time. So these are time for 25 oscillations without changing anything, right? But due to some like errors or due to some negligence, these values can slightly change, right? You won't get this, like let's say you might get these values 50.1 seconds, another one 51.2 seconds. If you get a value that largely differs like this, right? You have to neglect that because there is a large error here, right? You can neglect that. Then you have to again do the experiment till you get a closer value. So these three values should be like this, right? Then for these values, you need to get, what you need to get is time for a one oscillation, right? So to get a one oscillation, you have to divide this by 25, right? You have to divide this by 25, then you can get T1 time period. For this one, T2. For this one, T3. Now we have three different values for time period. Then take the average of these three. How do you get the average? Just divide by 3. You have three values. You just divide by 3. So what do you get? You get a more accurate value, right? For this length, let's say 1 meter, for this simple L, you did the experiment 3 times. Same thing, right? Without changing anything. Then using these 3, you get a more accurate value for time period, right? Then next one, what do? You increase the length, let's say to 1.2 meters now. Then you do the same thing, right? You do the same. Get this, then take the average. Likewise, you have to get about 6 L values, 6 time period values for 6 L values in order to draw the graph, right? So these are the what they ask in the exam, right? So here the graph is drawn between what? Not simple n and capital T. We draw the graph between simple n and t squared, right? Then the values you got here has to be squared. So you get t squared values here. You can get, then you have values for t squared, values for L, then you can draw the graph, right? You can draw the graph. Just take down this table, thumbs up once done. If you have any problem, let me know. So if you want successfully get the like full marks for those structured essays, you need to have this much in depth, right? You have to understand this precisely. Once you have taken this down, please thumbs up, right? Okay, I think you understood this completely, this table, right? Draw a line here, draw a line here, then I'm moving on to the next fact. Then I'm going to talk about this something called locating pin. Write down locating pin. Okay. So why do we need a locating pin? So as you are measuring the time period, you need a locating pin to have a certainty of oscillations, right? So if this is the bob, the locating pin, it's something like just a pin like this. It is attached to a cork, right? This locating pin should be at the lowest point. You know that this oscillates like this, right? It oscillates like this. Locating pin should be here. Lowest point behind. Because if the locating pin is like this, you cannot clearly see whether it completes, passes, whether this string passes the locating pin or not, right? So the string is here, locating pin should be behind and at the lowest point, lowest possible point. So it cannot touch the string, right? Otherwise it would disrupt the oscillation. Locating pin should be behind the string like this. Understood? So this is the locating pin. So what are the requirements? It should be behind, just take this down, behind, directing to string. They asked this, right? That's why I'm giving you at the lowest position. Put a point here, then write down. To determine the turn of oscillations, the turn of oscillations, to determine the turn of oscillations easily and starting and stopping instances of stop clock locating pin is useful. Locating pin is useful. Okay. Right. So the oscillation happens like this, right? So you have to place the locating pin at the lowest point and direct into the string. You cannot put the locating pin here, somewhere here, right? You have to put that at the lowest point. There are reasons for that. I'll explain those. You have to place the locating pin here, right? Okay. Below that, write reasons for placing the placing the locating pin. Reasons for placing the locating pin at the lowest point. At the lowest point. So there are mainly two reasons for that, right? First one, you may have heard this one, right? Write down maximum speed of pendulum. Maximum speed of pendulum is at the lowest point. Maximum speed of the pendulum is at the lowest point. So you know that, right? This is just, okay, first take it down. Maximum speed of pendulum is at the lowest point. Okay, so if they ask, why do you place the locating pin at the lowest point? You just say maximum speed is at the lowest point. You know, this is a simple harmonic motion. So this is the center, right? Center has the maximum speed. Okay. But why is that? What's the reason? Do you understand what's the reason for that? Having, what's the advantage of that? Like, how can you justify that advantage? This is the reason, right? So if they just ask the why it is at the lowest point, you can say because it is at the lowest point has a maximum speed of the bob, right? The reason is that uncertainty of the time measurement is less at higher speeds. So let's say like this, right? So let's say this is the oscillation, right? So at the lowest point, I'll just draw two positions of the bob, right? As this oscillates, at the lowest point, this has the highest speed. So time between these two positions, let's say that is delta t1, time between these two, delta t1. Because this moves quickly, delta t1 is the error due to uncertainty, right? Because we are the ones measuring, right? Once this pass this point, you have to start the stop clock. Once this pass this point, you have to start the stop clock, right? But you don't know whether to start it here or here. But that difference is very is small if this moves fast. But what happens if you do the same thing somewhere here? Here it takes a longer time. So that time difference due to that uncertainty is larger for this case, right? That's why you go for the lowest position. Okay, just draw this one. Draw this one. If you are done, thumbs up. Okay, write down error due to uncertainty. Error due to uncertainty within brackets delta t. Error due to uncertainty is smallest at the highest speed. At the highest speed. Okay, so that's the first one. Second one, right? Write down. Since the amplitude of oscillations amplitude of the oscillations decreases uh, the bob would not the bob would not pass the locating pin. Would not pass the locating pin. So let's say, even though we say that there is no air resistance, there's air resistance, right? So when we are taking this for 25 oscillations, what happens? Practically, if the oscillations initial like this gradually decreases, right? Due to air resistance. So what happens if you place the locating pin here? You won't be able to take the oscillation, right? Determine that particular oscillation, right? But if you place a locating pin here, you can make sure one oscillation even after all the 25 oscillations are done, right? Understood? Okay, just quickly draw this. If you have done thumbs up. Right. There's a one more point, right? There's a one more point. Okay, let's say now you have started the practical, right? So so the moment this passes this lowest point, do you start counting? Like you have to take for 25 oscillations. Do you start from 1? Like once it passes, you, you don't say 1, right? 1, 2, 3, I mean 1, 2, 3. Likewise, you have to keep doing this for 25 times, right? But you don't start from 1 here, right? This oscillation, because we are personally measuring that, right? It can cause a personal error. As this oscillate, you have to get used to the rhythm of this. There's a rhythm here, right? You have to get used to the rhythm. So what do we do? In order to get this one, let's say you measure this from 3, 2, 1, 0, 1, 2, likewise up to 25. Once this passes, once you say 0, you start the stop clock. You start the stop clock, right? Then you say 1, 2, 3, 4, 5, 6, up to 25. At 25, you stop the stop clock. So that's how you take simple T measurement, right? So you have to stay focused, right, while you are doing this experiment. So how do you say? 3, 2, 1, right? As it passes 1. Still you did not start the stop clock, right? What do you do? 1, you say 0, then you say 1. 1. When you are saying 1, you start the stop clock. 1. 1, 2, 3, 4, up to 25. Once this passes 25, you stop the stop clock, right? So that's how you take the time measurement. Okay. Uh, Draw a line below that, right? This point. When you are taking the time simple within bracket simple t measurement, time simple t measurement, the counting starts, counting should start like this. Just write this one. 3, 2, 1, 0, 1, 2, up to 25. When counting 0, you start the stopwatch. You start the stopwatch. Uh, then next line, counting started from 3. Counting started from 3 for the person. For the person, no, when you are saying 0, when passing this point, you start counting, right? For the person to get used to the rhythm, to get used to the rhythm, personal error, personal error is minimal. Personal error is minimal. Okay, so you start counting from 0, right? Because 0, then 1. Because you start counting when you are saying 0, then 1 oscillation, 2 oscillation, like that. Understood? 0. You say 0 here. You say 3, 2, 1. As, as this point passes 0, passes, you start from 0, right? Because for one oscillation, you have to count the time. It starts from 0, right? Time starts from 0. Understood? 0, you start the clock. 0, then 1, 2, 3, 4, up to 25. Okay? Right. Okay, so this is all I have to talked about this experiment, right? 10th experiment. Then write 11. 11th experiment. It doesn't take that much time now, right? Put the number 11. Then write down verification of the relationship between verification of the relationship between the mass of a body, the mass of a body suspended from a helix spring, a helix spring, and its period of oscillation, and its period of oscillation. So this is a similar practical to the one I discussed before, right? This is similar, so this won't take that much time, right? So for this experiment, you can take this down. You have to use a stand like this. There's a clamp. You hang it here. Then you have the helix spring. Now the locating pin is here like this, right? I'm not mentioning materials and apparatus, those stuff, right? Because those are already in the book, right? So what do you do in this experiment? So this is the stand, right? This is the stand. Then you hang a helix spring. Then you put some weights on this, right? Weights on this. Then that spring is stretched. Spring gets stretched, right? Depending on these weights. Then to the equilibrium position, once this stops, right? We are not oscillating this yet. We have to first find the equilibrium point. When this is at rest, this extend and comes to rest, right? Then you have to place the locating pin here like this. Okay. Then what do we do? You give this a small, then you extend this further, then release. Then it starts to go on a simple harmonic motion like this, right? Using the locating pin, you can determine those oscillations, right? Similar to the previous one, right? So the previous what we discussed applies to here as well. Okay. So we don't have to discuss that much on this experiment. Okay. So do you remember the time period for this one? This equation, right? T equals 2 pi mass divided by K is what? K is spring constant, right? If you don't remember, take those down. K is spring constant. Simple M is the loads applied here. Mass applied here. Simple M divided by K, 2 pi. That is time period. Time period means this goes up. It has to complete one cycle. Goes up, comes to the original position. Goes up, comes to the original position. So that is a one time period. Here as well, you have to take for like 40 oscillations in order to minimize the fractional error. Everything discussed earlier applies here, right? Okay. So if you read, you can take this equation down. So if you read the title carefully, what do you say? Verification of relationship between mass of a body, that is simple M, and time period. So this experiment, target of this experiment is what? To say that this equation is right, correct, right? So how do we say an equation is right? Whenever you have to make sure that an equation is right, you have to go for graphical method, right? So that is the another reason for going for graphical method. There's no any other experimental method to say that the equation is right. You cannot just put two numbers and say that this equation is right. You have to verify the equation, right? To verify the equation, in any case, you can check any practicals, right, on the book. For all the verifications of equations, you always have to go for graphical methods. You always have to go for graphical methods, right? Here the same. Right. Here we are not going to find simple K or anything. We have to verify this, right? That's the reason for using a graphical method. Below that, right? Why graphical method? Why graphical method? Below this, right? Here, the target is not, here the target is not minimizing, the target is not minimizing the random error. The target is not minimizing the random error. Verification of equations, verification of equations experimentally must be done using graphical method. Okay, using graphical method. I have to say the same stuff, right, in this experiment as well. I'm not going to, but I'll explain some. Okay, so here also I can say like this, right? Root m, you can take root m as x and t as y. But what's the problem here? This is less accurate, right? Same as before. That's why we have to square both sides. To prove that we need error analysis, right? That is out of the syllabus. But saying this is more accurate is enough. 4 phi squared divided by k m. So this is used as y, this is as x, and this is as m. This is more accurate. Take it down. So we square this both sides, right? Then we have to get 6 readings for each t squared and simple m. Simple m is the mass applied, right? So let's say you put a 1 kilogram here. Not a 1 kilogram, right? It is like 50 grams. For an example, I'll take, you put a 1 kilogram here. Then, same as before, you have to take the time measurement for 25 oscillations. So let's say, for simple m, you put a 1 m here, then you get time measurement for 25. So you do that for 3 times, right? Then you have to determine that for one oscillation. Then you divide by T1 by 25 or 40, right? Whatever recommended. So T1, T2, T3. Then what do you get? Then you get average. That is T. Then you get T squared. If you want, you can write this with me. T equals T1, T2, T3 divided by 3. Then you need to get T squared. So likewise, all you have to do is just increase. So once you do this, so now you have done this experiment 3 times, right? For a one mass without changing anything, then got the average value, then got the t squared. Then you have one value, right? One coordinate. T squared means y, m is x. Then what do? You get 6 such readings. You have to repeat these. It is like you have to do this 18 times, right? Understood? You have to measure. It is not that easy. You have to do the same thing. Same thing means by slightly changing m, you are taking 18 time measurements, right? In order to get this. So once you get that, so you have t squared values here and x values here. You draw this graph between t squared and M. Then you have 6 coordinates like this, right? Then what do? You draw the best fitted line. Best fitted line, the line that goes uh, right in between, right? These coordinates. So if you get a straight line, what does it say? This is a, if you get a straight line which goes through the 0, it is proved that this is y equals mx. Now y equals mx is justified, right? So if this is verified, this is verified. If this is verified, this is verified. You go back. So that's how you do verifications, right? That's how you do verifications. Okay, take this down. So the same things applied, right? Here, for taking time measurements and all those stuff. You start from 3, 2, 1, 0 like that, 0, 1, 2, then 25 like that, right? Everything applies here. Okay, right. Uh, below this, right? Below this whole thing, right? All the important facts are discussed. All the important facts are discussed under 10th experiment. Under 10th experiment. Right? So that is all the theories. Then I'll move on to doing a few past paper questions. Okay. So if you have chance, I mean, I don't know whether you have done this experiment at this school yet or not. But if you understand this, these are the like many times they ignored these. That's why this experiment seems like not that scientific, right? Sometimes you may feel that experiments are not that scientific. They are just taking values from here and there, but everything has a reason there, right? Taking there, this experimental side is a whole another side of physics. Okay, there are two main parts of physics. That is theoretical physics. Theoretical physics is that's what we are doing when you are doing questions. That is same somewhat theoretical physics. Another part is experimental physics, right? When you are going for like a PhD or something, those are two branches: experimental physics and theoretical physics. So this experimental side is, so everything given in theories must be proved using experiments. Otherwise, those theories are not considered valid, right? Those are just theories. That's why these experiments, they give a very important position for these experiment questions, right? Okay. Uh, then we'll do some questions. Just download, I sent you that a separate one that is 2006. Do you have that? Take that PDF, 2006. It is in the group. So simply part 1. So they are asking just for the expression for time oscillations, obviously this one, right? That's easy. Second part, rearrange the above expression in the most suitable manner in order to obtain a value for g by plotting a graph. Most suitable manner, right? Okay. So you have to square. When they say most suitable manner, this manner. You cannot put g here. You have to put g like this. So this becomes y, this becomes x, this becomes gradient. Here the b is at the lowest point, right? I don't know whether the diagram is tilted, but b is the lowest point, okay? When taking readings for t, reference pin directed at point B shown above diagram. Why the directing of this B gives a better accuracy for time measurement than directing at A. That another thing is you should be able to form sentences to say what you mean, right, correctly, to convey your idea. So that comes with practice by doing questions, right? So what do you say there? Hmm? So for the better, you can just say at B, Bob has the highest speed. They don't expect further clarification why this is. You can just say at B. If they ask, you can say, but this is enough, right? At B, Bob has the highest speed. If you want, you can write due to less uncertainty. I mean, uh, due to minimal time error of uncertainty, right? But here that is enough. Anyway, you have to answer exactly what they say, right? Okay. Part 1. Student measure the time for only one oscillation. That value is given as 2 seconds. Instrumental error. So that is the least count, right? That is delta t. They said 0. What? 0.1 seconds. Percentage error. So how do you find delta t divided by t? This is fractional error of time period, right? Not time measurement, not time for 25 oscillations. This is for time error for uh, time period. Make it a percentage error, you have to multiply that by 100%. So delta t is 0.1 to 100%. 5%, right? Then at the second part, then he measures the time for 50 oscillations. Sorry, 25 oscillations. He gets 50.2 seconds. And here as well, least count, we are using the same measuring instrument, right? So the least count is 0.1 seconds. Then again you have to calculate percentage error. Delta t divided by t 100%. Zero 0.1 divided by 50.2 times 100%. Here you don't have to use logarithm, right? Do you see that within brackets they say only to first decimal? Accuracy is required only to first decimal. So if they ask that, you can consider that this to be 50, right? This to be 50. Because 50.2 will give a different value for like second, third decimal or second decimal. For the first decimal, we get the same value whether it is 50 or 50.2, it doesn't matter. So better to take 50 there. You only need the accuracy for the first decimal. So if it is 50, it is 0.2%. That is the fractional error. For the measurement of, for how many? 25 oscillations, fractional error is 0.2. Here the fractional error is 5%. Okay. The recommended fractional error is, it should be less or equal to 1%, right? This is okay, 0.2. This is not. That's why we take for 25 oscillations. Okay, in the part C, they are saying that the bob has a radius, right? So you have to rewrite the expression. So what is that? T equals 2 pi. Instead of L, you have to put what? I told you that it should be the distance to the gravitational point, right? Center of gravity. So it should be, instead of L, it should be L plus R divided by G root. Actually, you have to rearrange this. Rearranging means you have to make this in order of y equals mx plus c. So here the x variable is length, right? Length of the string. So take L out plus, then multiply this 4 pi squared r divided by g. So this is y, this becomes m, this is x, and this is c. Okay. So this is the answer for first part. Then second part, determine simple g. Determine simple g. So once you draw this graph, you can get gradient and the intercept, right? So in order to determine g, you can use gradient, right? Not intercept, because intercept has simple r. We don't know value for simple r, but everything in the gradient we know. So to determine simple g, we can find gradient. Gradient is given, right? Gradient is given as 4.0 s squared per square meter. No, per meter. So 4 phi squared divided by g equals to 4. These simplifications are easy, right? They don't make it complicated. Simplification is easy. But some cases they might give a complicated, but rarely, right? So if they take this pi to be 3.1, take it to be 3.1, right? You have to follow exactly what they say. Don't write 22 over 7 or something. You have because they are saying a convenient method. They are giving you a hint, right? So if you follow those, you can easily conveniently get the answer, correct answer. You have to follow exactly they say in the question. Okay, 4 cancels off. Cross multiply g is equal to pi squared. Pi squared means they say 3.1. You can easily multiply 31 by 31, right? So 1, 3, 3, 9. 961. So two decimals, there are two decimals. So it should be 9.61. This is G. But if you put 22 over 7, this gets complicated, right? Understood? We don't need any complications. Okay, then you have to find the radius. To find the radius, you need to go for the intercept, because intercept includes the radius. So 4 phi squared r divided by g is equal to what? 0.04. Right. Here also, when you are doing the calculation, you have to do it simply, right? Don't make it complicated. You always have to go for a search for a easy method, right? So if you think about here, what is G? G is pi squared, right? You got that. You can use that here. Then pi squared cancels off. But if you substitute pi to be like 3.1 or something, then this calculation gets complicated, right? So in the exam, that's why you take students complain all the time that they don't have enough time, right? The reason is the lack of knowledge and lack of practice of doing questions, right? So pi squared cancels off, then 4r is equal to 0.04. So r is what? 0.01 meters. So that is a 1 centimeter, right? So radius of the bob is 1 centimeter. Right. In the part D, they say instead of a metal bob, so what we use is a metal bob, but student uses a wooden bob. So what happens? A wooden bob it has less density, so it has a less mass. I mean, yeah, mass is less, right, for a wooden bob. So what happens if it is a wooden bob? We give this oscillation, half mv squared. If this has less mass, the energy contained in the bob is less. So what happens? So there are drag forces on air, resistive forces. If the wooden bob has less energy, its oscillation would quickly stops, right? Understood? Its oscillation quickly stops and it comes to rest, and we cannot do the experiment then. you can write a reason, but it has to be just reason, right? You should be able to justify that, right? You can be creative and write that. If it seems correct, they cannot reduce marks. But you should be able to justify that. So you can write energy stored in a wooden bulb. Energy stored in a wooden bulb is less compared to a metal bulb. Is less compared to a metal bulb, right? Okay, so that is the experiment. The question on 2006. Then I sent you a PDF. Check that another PDF. Get the 2008. 2008. All the practicals are included there, right? Take 2008. Okay, 2008. We have this spring, so you don't get the exact experiment, right? There can be slight deviations. So you need to measure the extension of the spring. So this is given. So how do you place the ruler? It's placed like this, right? So this is the meter ruler. Mark these calibrated marks. So this becomes the meter ruler. Okay. So that is what you have to draw. Okay, simple B part. Simple B. Extension versus load. Extension, there's a factor 10 to the power minus 2 meters. Load is 10 to the power minus 3 kilograms, right? So whatever the coordinate you take, you have to multiply that by these numbers, right? If it is a mass, 10 to the power minus 3. If it is extension, 10 to the power minus 2. Okay, so what do they ask? So using this graph, so this is a graph between mass and extension, right? Remember this equation? This is the spring constant, okay? So they ask you to determine spring constant in kilograms per meter, right? So you have to get the gradient of this graph. Actually 1 over gradient becomes the answer there. So listen now, right? This is important. I don't know whether you know this or not. So when you get a graph, I didn't explain this. So this is applicable for all the graphs, right? For all the experiments. So when you are calculating gradient of a graph, you have to get two xy coordinates. You have to get two xy coordinates, right? One coordinate here, one coordinate here. Let's say x1, y1, another one x2, y2. So what is the gradient? Difference of y coordinates divided by difference of x coordinates. Then this gives the gradient, right? So there are rules when you are taking these coordinates. There are rules, right? You cannot choose these two coordinates to be very close. You have to use the whole graph. Another thing is, you can see the squares, these lines. The graph must go through intersect of the square net, right? You cannot choose these points, right? If it is fractionally intersects, you cannot use that. The graph should exactly go like this, right? So if you consider all those, you can find the most appropriate 2 points on the graph. So this point, the most appropriate point is x coordinate 70, y coordinate is 9. 70 and 9. Sorry, 72 and 9, right? 72 and 9. Sorry, 72 and 9.3. This coordinate, if you carefully look at 72 and 9.3. Another coordinate is this point. It is 9 and x coordinate is 9, y coordinate is 0.9. Okay. So these two are the most appropriate coordinates in order to find gradient, right? So these are the distances points, right? These are the apart points, most apart points, right? There are some other points here as well, but you can take this as well. They would give marks. Right. So using these xy gradients, you can find the xy coordinates, you can find the gradient. How do you find the gradient? So xy, y is 9.3 minus this y is 0.9 divided by x, 72 minus 9. So you know y coordinates must be multiplied by 10 to the power minus 2, right? Then x coordinates must be multiplied by 10 to the power minus 3. So what is the unit of this? Y divided by x. Y is measured in kilograms, x is measured in meters. So the kilogram divided by meter. You get the gradient as 63 divided by 84 kilograms per meter. You get the gradient like this. 63 divided by 84 kilograms per meter, right? But the spring constant, they ask the spring constant in terms of What? Sorry, not kilograms, meters per kilogram, right? Here, these are the lengths. These are m. M means x coordinates. Y divided by x, meters. You get the gradient in meters per kilogram. But you need the spring constant in terms of kilograms per meter. Here it is not newtons per meter. They say it is they ask that in terms of kilograms per meter, right? So instead of newton, you have to take that in terms of kilogram, right? Not newtons per meter. So when you divide this, 63 means 63 has 7 nines. No. 1, 2, 1, 8, 3, 4. So it is 3 divided by 4, 0.75 meters per kilogram. So this is the gradient. So it is obvious spring constant should be 1 over gradient, right? Spring constant is 1 over gradient. So it is 1 over, no, here you get 84 divided by 63. 84 divided by 63. So you get 4 over 3 kilograms meters per kilogram. Here spring constant is 1 over gradient, meaning 4 over 3. So you get 3 over 4 kilograms per meter, which is 0.75 kilograms per meter. So this is the spring constant, 0.75 kilograms per meter. Then at the second part, they say clearly indicate on the graph the 2 points which you have used to determine K. So you can put these 2 points, right, as P and Q. This point and this point. Okay, then take part C. Try part C. Okay. So they have given, so instead of this equation, they have given a modified equation, right? So if they say take this equation, you take that equation, right? You don't have to argue with that equation. You just follow everything they say in the question, right? So they have given a modified equation, and because it is spring constant and multiplied by G. Remember, we got the spring constant in kilograms per meter. To make it Newton, you have to multiply by G, right? That's why there's a G here. But you don't have to think about those stuff, right? You just take the equation, whatever they say, right? Then all you have to do is, you just have to arrange this in order to draw a graph. So what do we do? You make it squared. 4 squared, m plus divided by kg. Put kg here, right? You square this and put the kg here. Then bring out the brackets. 4 phi squared capital M divided by kg plus 4 phi squared kg m over 3. So this one you can take it as y. This one you can take it as gradient. This one as x. And this whole thing is c. Now you have rearranged this. Because of this term, there's a intercept in the graph. So this is the first part of C. If you have a problem, let me know, right? See first part. Second part. What additional instruments do you need to take measurements in this experiment? So in the experiment, so they're asking what are the measuring instruments, right? You have the meter ruler. So what is the another measuring instrument? Stopwatch, right? They haven't mentioned a stopwatch earlier. They have a meter ruler, but they don't have a stopwatch. So stopwatch should be the answer for the second part. Then the third part, what quantities would you extract from the graph to determine G and M? So you have to determine G, right? We already have calculated K. K is we found, right? So K is known. So to determine G, right? Yeah. You don't have to know about intercept because intercept has an unknown simple m. Simple m is the mass of the spring, they say. You don't know simple m. So to determine simple G, you can determine that using what? Gradient only. So if you substitute values here, you can find G. Got it? They are not asking for the calculation. So the only unknown in the gradient is simple G. So you can find that if you know the gradient. Then you need to determine mass of the spring. Simple M. So this equation got modified because they considered the mass of the spring. In the experiment, right? In the experiment in this book, this mass of the spring is considered to be negligible. But here they consider that, right? If they consider, they give you the equation. You don't have to remember this, right? They give you the equation. Then you just have to follow the instructions they say. Okay, so to determine simple M, what do we need? Simple M is included in the intercept. So simple M can be found using intercept. If the intercept is known, only unknown in this term is simple M. So you can find simple M. Understood? Thumbs up, right, if you understood. So let me know if you have any problems. Do you have? If the percentage error of mass value is 1%, how many oscillations would you need to take in order to match the percentage error of time period also to be t? And they have given an equation for percentage error of time period, right? So you have to use that equation, right? So they say this is the fractional error of time period. There's a 2 as well, right? You don't have to think about that. If they say so, you have to take so. So you know that 2 delta t over t is equal to what? Delta simple t over t. Earlier, remember? Delta t over t is equal to delta t over t. We got that in the note, right? So instead of delta t over t, you can put delta simple t over t. And there's 2 here. So what they ask is how many oscillations required. So this error is 1%. So this error has to be 1%. 1% means if you write it as a fraction, it is 1 over 100, right? 1% means 1 over 100. So error in the measurement, that is the least count, is given as 0.1 divided by time. What is this simplicity? Simplicity is equal to n times oscillation. So n times one oscillation takes 2 seconds. So this is 1 over 100. Then 2 cancels off. If you cross multiply this, n is equal to 10. So in order to make the error of time period to be 1%, you have to at least take 10 oscillations, right? 10 oscillations. Okay, take it down. Once you are done, thumbs up. Okay, then part E. So a student use a brand new spring. Then they say on the figure given below, sketch the shape of the graph that you would expect in this situation. So for the usual spring between E and M, you got a graph like this. If the spring is brand new, you have to think about this practically, right? If the spring is brand new, it is very hard to extend that, right? Initially, it's a bit hard to extend. So what happens, even though we increase the mass or the weight on the spring, extension, there's no extension. But the extension causes after certain value of capital M. Like that, right? If you have experienced a brand new spring, even though we apply force, there's no extension initially, right? Extension is 0. So the graph should be like this. Okay, just draw that one. After, later you can try these questions again, right? Only way to get this, you have to practice doing these questions. So for structured essays as well, you have to separately practice for those. Same as MCQs and essays, right? So at home, try this one, right? 2015 A-level. So this is based on simple pendulum, 2015 A-level question. And if you have any problems regarding this question, 2015, please let me know. Send me a message, then I'll explain that. So on tomorrow, I'll be discussing of, tomorrow 8 p.m. I'll discussing of sonometer. So sonometer also has 2 practicals. Based on sonometer, there are 2 practicals. There are many questions. Oftentimes, they ask questions based on sonometer, right?